finally talk about that, about her work. I mean, we thought about having her before, but she was writing her thesis and she was busy with everything on the PhD. But now she's here finally to talk to us about graph neural networks and cosmology.
So, hi guys, thanks for this nice introduction. Well, some of you already have heard about this work. I hope that you are not so, I don't know, bored about having me here to hear about this one once again. But then, well, I'd like to talk about how to try to do cosmology using graph neural networks. And well, to start this presentation, maybe some of you can try to say, oh, you can try to do something different, but I'd like to try to motivate this, talking about that, oh, we still don't have the perfect summer statistic to deal with our scales, right? For example, if you think about the power spectrum, what happens is when you try to estimate the cosmological parameters, we are mostly taking care of the information corresponding to the larger scales. We mostly throw out all the information which are related to the small scales. And using these graph neural networks, we're trying to explore a way to try to extract cosmology from our scales. And how we are doing this? Well, suppose we have a bunch of galaxies here with all that information. We're trying to translate this into a graph. And then we're feeding these to graph neural networks, a machine learning black box. And then we're trying to estimate the mega matter. So before talking about this, I don't know if you all know about graphs, but graphs are really interesting things, are mathematical units composed by nodes, edges, and then we have like one global property, for example. So the nodes contains their node attributes, the edges contain their edge attributes, we have a global property, and then the graph can be represented by these three numbers or arrays, if I can put it this way. So it's really interesting to use graphs to do things in physics because I have really a way to take care of lots of things. So the first thing is like, oh, we can take care of structured data. We can have graphs which have like their same relationships. So if you think about, oh, we are going to consider node attributes which are related to the galaxy properties. So all the graphs are going to contain their node attributes with these properties. So they are, in some sense, structured. So that's it. And we can also take care of irregular data, which means that we can have a graph which contains a number of objects which is different from the others. Okay, so if you think about galaxy catalogs, we can take care of one galaxy catalog with 1,000 galaxies, and then the other graph is going to take care of another catalog with tens of galaxies. Okay. More than that, graphs take care of some properties. For instance, permutation. They are permutation invariant, which means that if you think about the permutation matrix acting in a function, right? We are not like changing this function. And then in the context of graphs, this means that if we change the positions of the nodes, we are not changing the global attributes of the graph. So more or less, these are the graphs. And then we're trying to do cosmology with galaxies. And here we're trying to build these graphs using our galaxies. So the nodes are going to be our galaxies. And then the node attributes are going to be the galaxy properties. In this work, more specifically, we are considering as galaxy properties the z component of the galaxy velocities. Why? Because we like to do this with real data. And in real data, we can only observe the velocity at the line of sight. And then just for simplicity, let's consider the z component of their velocities.
And okay. The angular position also considered?
Yes. The positions enters when we try to build the edges. So there's no like a direct prescription to really obtain the edges, but everything can be translated into graphs, right? And in galaxy catalogs or halo catalogs, we have the positions of their objects. And then let's try to get these connections considering these positions. So imagine that we have a galaxy here, and then we have these other galaxies around. What we are doing is, oh, let's try to roll a sphere around this red galaxy here. And this sphere is going to contain a radius. So we can imagine any value that we would like to consider. But then let's say that all the galaxies which are inside this sphere are going to be connected with this first one. So this is the way that we found the edges for these galaxy catalogs.
This is not a cluster-finding algorithm, it looks like.
We can, yeah, we can also use, for instance, a KNN to do this job as well. But there's something which, like, at the time that we are working on this project, we realized that if we use, for instance, a KNN, we can say, oh, we're going to connect 10 galaxies around this galaxy, here. Okay, the box is here, or sorry, these galaxies are here, and the others are here, here, and here. So if we grow up this sphere, these are the galaxies which we are connecting, right? So if we think about the KNN, if you consider a galaxy which is here, and imagine that we have a really empty space between this galaxy and these other galaxies which are really far away, maybe we are going to end up with connections with galaxies which are really far away from each other. And this is not a problem, but with this prescription, we achieved the best results. And it's another thing which is important to mention here is that every time that we are connecting these galaxies, we are taking into account periodic boundary conditions. And I will come back to this information in the next slides.
So the parameters are this radius.
Yes. So this is
How do you choose the galaxy, the first galaxy? Because say the blue galaxy, we also have a radius around it.
Oh, yeah. This is just a representation. Sorry.
Um,
Just a pictorial version. But every time that I try to do a presentation, I just try to draw things. But yeah, of course, we can draw this sphere around this blue galaxy, and then we can have other connections and so on and so forth. But it's like,
that's what you do in prep.
yes, in practice, yeah, that's what I do. This is not here and in the next figures that we are going to see, because I was taking too much time like trying to draw all the edges. But yeah, indeed, they are there. Sorry, they're on.
Yes. So just to see if I understand then, so the galaxies within these radius are selected by velocities. So all the
they're-
galaxies within that thing are supposed to have the same velocity or something?
No,
Find
sorry.
a graph, or is this?
We are just connecting the galaxies according to their positions. The velocities are in there, but
What, sir?
Position.
The position. So
positions.
you're selecting an area, or the galaxies within that are a graph?
Yes.
Okay.
Yeah. But the whole graph is the whole catalog. Sometimes if I draw things, this can be kind of confusing instead of like being something that can explain everything. But yes, indeed, each catalog is a graph for us. So in some sense, you can have galaxies which are like, these are not connected because I'm considering this a link. But in some sense, like the whole graph is the whole catalog. So sometimes that we are not going to have connections between this galaxy here and this other because they are too far away. But indeed, if we have a galaxy here and the other galaxy here, they are connected because we have periodic boundary conditions. But like in my drawings, like in the pictorial conversion that I'm presenting here, we don't have all these connections. Sorry about that.
But these galaxies can actually be far away because they can be in different redshifts.
Yes, but here we are only considering z equals 0.
We're just considering the angular position.
Yeah. Sorry, I jumped to another again. So, yes. That's it. Okay. So we are connecting these galaxies considering their positions, and then we can take into account some edge attributes as well. And we talked about these edge attributes, thinking about including 3 numbers. And these 3 numbers are going to be related to the positions that we already have, and they are taking care of translational and rotational symmetries. So these are the edge attributes. So for 2 galaxies, I and J, we have the modulus of the distance, not the modulus, right? Divided by this R link. You can put like another number here, but just this was just a matter of choice. And then we have like alpha and beta, which are 2 angles which are going to be responsible to take care of like these angular positions. So this is the distance. So we have the position of the galaxy I and the galaxy J, and this is the distance. That's it. And then I'm defining this delta here just to think about, oh, what is the difference between each one of these galaxy positions and then the centroid? for each one of these galaxies, for each one of these catalogs. And then we are computing this angle between these two galaxies corresponding to the centroid, and then this same delta, but then the angle corresponding to the distance between these two galaxies. So these are the edge attributes. Of course, you can think about other things to put here, but yeah, that was the prescription.
Sorry. So the centroid would be like the red blob, red galaxy in the example?
If you think about like the whole box, you are going to measure all the galaxy positions, and then we're going to measure this mean position, which is going to be the centroid. So if you only have 3, probably this should be around.
And this position is in redshift space.
No, we are just considering the positions of like the galaxies per se in the box. We are not like considering like really other things. So we only have like the galaxy catalog with these X, Y, and Z positions, and that's it. So each galaxy catalog is going to be converted into a graph. Of course, we can have more connections here, but this is just like a pictorial representation. Okay. And the other thing that we're taking into account is this global property, which corresponds to the number of galaxies that we have per box. Okay. So this is more or less the description about what are graphs and how are the graphs that we are building. And then we have to think about the graph neural networks, right? And these graph neural networks are these machine learning algorithms, which are responsible to give us some answers. Here in this work, we're trying to predict the development of matter. And behind this black box, what is happening is that we are using this message passing scheme, which is a really interesting way to really pass information, as the name says, between like the nodes and the edges attributes. So if I jump to this other slide, I'm going to tell you that we can use graphs to try to answer many different questions. So we can use graphs to do graph generation, to do link predictions, and so on and so forth. But here we are more interested to do this graph embedding that we are trying to estimate a global property for each one of these graphs. But we can actually use for many tasks.
Training neural nets or just unsupervised or supervised?
It's supervised.
So you need a training set, everything.
Yeah, I'm going to arrive there. But now it's just like message passing scheme. Is that right? Okay. So in this message passing scheme, actually, you can use many different architectures. You can think about using a bunch of combinations of like this graph convolutional layers, this edge convolutional layers, these side layers, or you can think about using these meta layers, which are really powerful. And if you take a look at the documentation, this is the way that all these other layers are mixed. Okay. And
The inputs, sorry, not inputs. The nodes are these graphs.
the input, like the data
Nodes,
input.
nodes, just the node.
Yeah, sorry. The data
Yeah.
are the graphs. So we are converting each galaxy catalog into a graph. Now I'm talking about the graph neural network, which is like the machine learning part.
Sorry.
Okay, sorry.
So
So-
the usual way of
Mhm.
this to you have an input layer, neural net, and then an output.
Yes.
You have the same thing?
Yes. I'm going to get there.
Oh, okay.
But yeah, these are the components of these neural networks. So you can build these neural networks using these neural layers. And these neural layers are usually built with these meta layers. Each one of these others are like built using these meta layers. But you can design your own architecture for this meta layer. This is what I would like to tell you here. But I think that in the next slide, things are going to be more comprehensive. If it's not, I can try to go there. But the message with this slide is like, these graph neural networks are really good because they are permutation equivalent, which means that any permutation that you do is going to be a permutation with your final graph after the machine learning part. And then it's really nice because we can think about using each one of these different prescriptions. But each one of these different prescriptions are going to be more important or going to be more useful according to the way that you built your graphs previously. So if you think about each one of the ways that each one of these layers work, we are basically updating values in our graph. So of course, we have the usual multilayer perceptron, the usual neural network there, right? And this thing enters with this H here. But before having this usual multilayer perceptron there, we are updating with this message passing scheme the values of the attributes for the graphs. We're not changing the shape of the graph. We are updating the values for the nodes, for the edges, for the global attribute. You can think about what you like to update according to your problem. And then you can choose the architecture. For instance, if you use this graph convolutional layers, we are updating the nodes only. And we are doing this update only considering nodes. So if you have this problem of these galaxies converted into a graph, and for us, it really matters the positions of the galaxies, and then we have the edge attributes there. If we only update the nodes, this is not the best architecture, right? So the same happens if you think about this other edge convolutional layer or even the side layer. Even though the edge convolutional layer considers, in some sense, the edge information according to this difference of each one of these nodes, we still have global information if we build our graph in the way that we have built before, right? So our graph contains the galaxy attributes in the nodes. The edges corresponds to the distance attributes as well, right? And then we have the global property, it's the number of galaxies. That's why we had to think about a different way to do this updating. And this other way was using these meta layers. So maybe with this representation, things can be more clear or not, let me know. And then I will try to see another ways to explain this. So the input information that we have here are each one of these galaxy catalogs translated into graphs. And now we are going to enter to try to see what is happening behind the graph neural network. So basically, the graph catalog is the same. We are just changing colors from each layer to the other. So we are changing the values for the nodes and for the edges. And we can have as many layers as we think about.
So each node in the, what we call it, the first layer, the input layer, each node is one of those nodes with these attributes.
I think that we are thinking about something like more related to the usual neural networks,
Yes,
right?
I'm
Yes.
a node guy.
Yeah, no, don't worry, don't worry. So it's a bit different because in like the usual neural network,
Yeah, the multilayer perceptron.
the
that's-
multilayer perceptron.
That's what I know.
Yes. So the multilayer perceptron is going to enter here after a while.
Ah,
If you where we can really see the multilayer perceptron.
that looks more.
But then, yeah. But in each one of like these updates, we do have a multilayer perceptron. But the thing is the following. We have our structure. Our structure, our data input, is our graph. And our graphs are composed by these galaxy properties, right? So we are going to think about changing the values that we have for each node attribute and for each edge attribute. And we do this by layers, right? And while we do this by layers, I'm trying to say that we are updating the edges. So each new edge is going to be updated considering the values of the previous node values, and then the edge in question. And here, this fancy symbol here corresponds to a multilayer perceptron, which concatenates this array, like the information in this array.
So if I may, I think if you want to understand in terms of the multilayer perceptron, and tell me if I'm wrong, you're thinking about a number, and the number talks to another number in the next layer, right? Through some links, which are some functions, right? So the point, the number now is a set.
Yeah.
That set is the graph. And the graph is connected to other graphs here through pretty much the same way, but of course, much more complex because you have a set now instead of a number. But that's basically it. Of course, technically it's a bit different, but that's basically, it's more complex, but it's one layer to the next layer. That idea is still the same. You have still the layers.
Yeah. We still have the layers there, but the input information which we have per layer
Yes.
is this information update.
Yes.
And well, this is really nice because before, instead of like having the graphs, we only have like just one array with dimensions, right? And then we pass this information to get a number in the usual multilayer perceptron, which I can show here. So what happens here in this last part of the GNN is that now we are going to kind of forget about the information of the structure and then only take care of the values. And then we are concatenating all the information of these values, considering the nodes, which have been updated, right? And then the global property. And then I have another array here, which enters in this multilayer perceptron. And then this is like the usual idea of multilayer perceptron.
Right.
But before this multilayer perceptron, the information which enter here were like the values of the nodes and the edges to update each one of these nodes. That's why this is really powerful, you know?
But then you have to transform, so the dots, the circles are the
Yeah.
usual multilayer perceptron.
Yes,
So then you have to, those are numbers, you know, like
Yeah.
Joe was saying. So you have to transform the information in the graphs into numbers at some point.
yes. And this final multilayer perceptron, yes, indeed. But the thing which is like really interesting to think about previously was that we had all the information there, and in some sense, we have this information related to the structure already there as well, right?
The structure of the
The structure,
galaxies.
yes,
Yeah, that's what I was trying to imagine, suppose, because some information are in the structure, say, the baryon oscillation feature, for instance.
Mhm,
How do you see that in the graph language?
mhm.
It should be there, but they don't.
Yeah, yeah, so,
But this is
For
what
sure, this is a large scale thing, right?
Yeah,
The
that's
100 megaparsec, the linking length there is like 1 megaparsec, so small scale.
So, but
Not sure if
it's
it's,
among the different, because the whole catalog is there.
the whole catalog is there,
The
yes,
information of the baryon acoustic scale is there
in some sense.
in some sense. So, and that gives you, that's the physics of how to get, you know, like matter and stuff. This is-
but you don't take into account the distance between each graph,
Not between different catalogs, so,
between different graphs.
yeah, no.
No,
No. Therefore, this information is not there.
so I don't understand.
What do you mean? It's on small scales, it's not on large scales. That's the whole point, right?
Yeah, but then you're getting information, say, on modular parameters.
Right.
That depends on large scales. So,
Who says?
well, the BAO scale depends on the
Who said
cosmology.
the BO scale is the only thing?
It's one.
Why,
of the
why do you
things.
think
I'm
that?
not sure.
So for instance, don't you know, you know for sure that the mass function depends on cosmological parameters, right? So
Yeah.
that's on small scales, you can measure that mass that has no information about BAO.
Okay, so you're saying that you're throwing away information of large scales in this analysis.
The information is there.
She's not throwing away, she's just
She's
looking
not
at,
considering.
she's not considering.
Okay,
Yeah.
not throwing.
She's looking on small scales, yeah, that
Yeah.
was her first slide.
Yeah, so, yeah,
So you're not considering large scales, okay.
Well, it's not directly there. I mean, your graphs have a linking length of like 1 megaparsec. So the largest graph that you can have is maybe the size of a
numerical.
large galaxy cluster. So
Right.
that's the largest scale, which is in
Right.
this.
So there's some information that they're not taking into account. That's what.
Or- Yeah, but the whole point is that nobody takes that information into account.
I understand,
That's the point.
I understand, but if you want to make cosmological analysis, what you want to do is to take all the scales into account.
Sure.
So this
Yeah.
has to be complemented
Yeah.
with something that takes into account.
Yeah, but
The question
but
is,
since-
can you do the two things into one?
Ah, right.
yeah,
First, you have to do the information on small scales, which
And nobody does.
nobody does.
Yeah.
So is there information? That's the first question, right? So.
yeah,
Yes,
Because maybe if there isn't anything,
yes,
then there's no point in going to those small
yes.
scales. right?
Now, what I'm trying to say is that suppose you get omega matter.
Mhm.
But then you get omega matter based only on small scales. And there is information on large scales that are not considered.
Yeah.
So at some point you have to combine this analysis
mhm,
with some analysis that take into account large scales as well.
Mhm.
Or can include everything here somehow, you know?
yeah.
And I don't
For
know.
instance, trying to incorporate information related to the larger scales to these small boxes that I will present in the next slides. But yeah, we are not there yet.
Okay. I understand better now, thanks.
Okay. So the main point here is like we have converted our graph, like our galaxy catalog into graphs. We have updated all our values. Now we are going to obtain the first and the second moment, so the posterior distribution for omega matter. And we are doing this modifying the loss function in this way. And then we are estimating omega matter for each one of these boxes. So the data set that we're using here are these camel simulations, which are really nice because they are like this data set to do machine learning. And well, of course, to have like many runs, because this machine learning, we need lots of data, these boxes are really small. They're only 25 megaparsecs per each. Okay. But they allow us to have many variations, for instance, in some cosmological parameters or even some astrophysical parameters. So we have access to omega matter, sigma h, 2 parameters related to supernova feedback, and 2 parameters related to AGN feedback. So we are training our machine learning algorithm in these boxes that we call as L8 set, which follows for Latin hypercube. And then we have access to different boxes that were run using variations of the 6 parameters and using different random seeds. So we are training the machine learning on these boxes from this L8 set, and then we are testing them. I'm just mentioning and giving this a name because if you go to use camels for your research, you will see that we have more than only this set. We have the Lightning Hypercube, the 1P set, and so on and so forth. I can tell you about them later, but in this research, think only about this L8 set. But then there are things that we are interested here, which is like, oh, in camels, we have access to many different hydrodynamic simulations, from Astro to Swift Eagle. And it's really interesting to have access to many different kinds of simulations. Because if you just take a look at one snapshot, this is actually a move. You can look about this move in the Camels YouTube channel from Paco. And then the thing here is like, oh, if you just take into account the same redshift here, it's not there later. If you think about this one snapshot for the same redshift, and here we are showing the gas density in blue and the gas temperature in red. And even though all of these different simulations were made to be the same simulation, okay, to have the same kind of properties from each other, if you just take a look, just by eye, they are really different. So we have regions which are way more hot in Simba than in Magneticon and in Lustrous and Astrid. And okay, if just by eye we can see these differences, should it be possible that we have a machine learning algorithm that could overcome all these differences and estimate omega matter? So this is in machine learning a problem that we call as robustness. And what happens is most of the times is like, oh, you train a machine learning algorithm considering one data set, for instance, these Astrid simulations, and you get good predictions if you have a good model, okay? Although, what happens when you change the data set to another one? What happens is that most of the times your machine learning model does not have power to extrapolate their predictions because of the differences.
Yeah, machine learning is not to extrapolate, it's to interpolate. That's
That's
what I understand.
Okay. You can put it this way.
In the sense that you should have the training set representatives of all of these situations that
Yeah.
if you don't, then you run into these problems.
Yeah. And if you have a model which is robust, then you can actually have good predictions. And if you have something which is robust, maybe with everything that we know, we could handle real data, right? So what we are trying to propose here is, okay, let's try to train a machine learning model in one of these simulations and see if you can have good predictions for these different data sets. So these other hydrodynamic simulations. And then here I'm just highlighting SB28, which is the same hydrodynamic model of Illustris NG, but now we don't have only variations to the 6 parameters here, but we have variations for 28 parameters. So a model trained in one of these others has never seen variations like universe like these other ones. And then in the case of Swift Eagle, we have a different way to find the hidden subhalo structures, which is Velociraptor, which is another code, which actually uses not only the positions of the objects, but their velocities as well. And Okay, these are like the best set of results that we have achieved, which corresponds to using only galaxy information of the 3D positions of the galaxies, and then the Z component of their velocities. And we have trained everything on Astro. And here, in these plots, I'm presenting to you the predictions versus the true values for a megameter, okay? And then the best set of results should be following this one-to-one line here. And well, as you can see, most of these values are following this gray line here. And we can actually take care of all these other metrics, okay? And see that in the case of root mean square error, it's close to 0. R2 is close to 1, as expected, according as well PCC. And then the results not biased, and then the relative error is around 10%, which is okay. And the reduced chi-square is around 1. So this model is actually working. The main idea should try to see if this produces good predictions to different data sets, which means that if we could have good predictions, we finally have for the first time a model which is robust. And this was what we have achieved, a model which produced good predictions no matter the data set that we have in account. So the subgrid physics model that we think about. And this is working in considering these SBT boxes, which considers many variations in these other cosmological and astrophysical parameters. And it's working on Swift Eagle as well. So no matter the fact that we have like these changes to find halos and subhead structures, we still get good predictions. At the time that we have achieved that predictions, we are really...
Oh,
yeah.
How do you estimate the error bars?
Oh, yes. So if we come back to this slide here, I was trying to tell you that at the end of the day, we are estimating the first and the second moment of each one of these predictions. So me here, there is like the value of megameter, so the point that we can see in the scatter plot, and the standard deviation, the error bars, corresponds to the second moment of this distribution. Of course, we don't have access to the shape of the distribution. We are just kind of like estimating two numbers from that distributions. And like that are the error bars. And well, we are really interested to think about where the information was coming from. And we tried to develop another machine learning or two kinds of machine learning algorithms, which would be supposed to take care of information corresponding only to the positions of the galaxies or only to the velocities, and see if only using each one of these informations we had good predictions. In the case of using only the positions of the galaxies, we just designed the same GNN that we had seen before, but without the node information. So we don't have the velocities. In the other case, we have a deep set. Deep set is more or less like the usual neural network. And then here, this means that we are not considering the positions. So we don't have like the edges. And while trying to do these two different considerations, we have obtained predictions like this, only considering the positions, or like these other ones, which are only considering the velocities. And this means that if we try to look about robustness, like we don't have like good predictions following this one-to-one line here. So the model was not robust. More than that, the error bars are larger. And by considering only the velocities, the model should be more or less robust, but we have like a large error bars, and even though we are not like following properly this one-to-one line. So in some sense, we have the model just does not work considering only positions or only velocities. We need both. So the information is coming from the phase space. And then we try to obtain a model which was better. So how in machine learning we can try to obtain a model which is better? We can try to use more information. And then we try to use, for instance, stellar mass, okay, as node information, as node attributes. Maybe this should achieve better predictions, right? And if you think about the model trained on Astro and tested on Astro, indeed, we achieved more or less a set of metrics which were better. The problem was when we tried to see the extrapolation. So we're not able to get good predictions for all of these other data sets, which means that we do have difference in this subgrid physics, which changes this other set of galaxy properties. And then maybe these GNNs are really extracting information from this phase space. So let me see here, just this is stellar mass. Let's just come back to this result and really think about, okay, if you are really extracting information from the phase space, and for the first time we have achieved a model which get good predictions for different subgrid physics, maybe we have a way to go a step further and try to use this on real data. And this is what we have been trying to do. But just giving one step back, let's think about how this model trained on Astrid was so good. So if you think about this plot here, we can see the number of galaxies in the y-axis. And then we can see the values of omega matter in the x-axis. Each one of these points corresponds to one box. Okay? Okay, so let's see what's happening. The model trained on Astrid contains a broader variation in catalogs, which contains from tens to more than thousands of galaxies. So a model trained here would be able to extrapolate across all these other models because it has already seen something similar on Astrid. But a model trained on Simba, Illustris, we're not able to see like boxes with a huge number of galaxies or even boxes with a really small number of galaxies. Take a look at Magneticum. We only have boxes with a really high number of galaxies. So maybe the number of galaxies is a driven component, like a really important component for these things. Well, maybe. There are other things which really matter for us and can be different kinds of trying to see what is going on with Astrid. If you take a look at some properties for these different hydrodynamic simulations for these different subgrid physics models, and we try to compare Illustris, Simba, and Astrid, we can truly see that in the case of the variations for the supernovae parameters, we do have a broader variation, okay? In the case of Astrid, what does not happen so well for the others. And together with this, we have the mildest AGN feedback happening for Astrid as well. Or if you take a look at the power spectrum of the hydrodynamic information with the dark matter, we can see that we have the lowest impact for baryonic effects. And well, Astrid has all this difference in the subgrid physics models. Maybe it could be a way to go to really try to represent our universe. And well, we have some hints that this is working better, at least for the purpose of doing machine learning. Well,
sorry, did you try to train on longer simulations?
Yeah.
And Astrid was the best.
Astrid was the best. If we,
The other one, bad or similar?
it depends. If we think about the boxes which are like in this like narrow things, they are like working okay. But if you go for catalogs with a higher number of objects or a low number of objects, no. In the case of Magneticum, we have really bad predictions. Yeah, and then there's something which is kind of interesting and thinking about trying to really think about information for other scales should be, oh, okay, we have trained everything using these small boxes, okay, only 25 megaparsecs. Can we really think about, think about having a bigger box, okay? Try to take just a sample of this bigger box and try to see if the information of this small sample could end up with some estimation for us for omega matter, at least. So in other words, we're trying to measure supersample covariance effects, trying to measure other modes effects. And the problem was that we found something really interesting. And the first thing was related to the fact that we are considering periodic boundary conditions. So, of course, when we go to a bigger box, we don't have like periodic boundary conditions anymore because the periodic boundary conditions are in the borders of this bigger box. The model was trained considering these periodic boundary conditions. And at the time that we have been trying to do predictions for small portions of this bigger box, we have seen a shift of all these predictions. So this is truth minus inference in the y-axis. And then we are like, oh, our predictions are not working at all. Let's just give up. But then I was trying, could be this an effect of only considering periodic boundary conditions to build the graphs? Let's try to give a step back and see. So I removed the periodic boundary conditions, and then we have the same shift for predictions for Astro and trained on Astro. Okay, but considering periodic boundary conditions in the training stage and then disregarding them. So we have trained the model, forgetting about the periodic boundary conditions. And then these are like the predictions that we have for randomly chosen subvariations of this big illustrious energy 300 with a side of 205 megaparsecs per age. And then we have these predictions for these different boxes. And as we can see, we don't have nothing which is perfect. If you take care of the metrics, we are really far away from the best values for the reduced chi-square or for the relative error. Although we took care on 100 boxes. If we just remove 30 of these boxes, the results are better. So as Paulo says, this is sigma clipping. This is not the perfect way of doing this, but things looks like as something which can be promising. Okay. So these are like our attempts to see supersample covariance effects. And these are the bad news. In these estimations, we have been trying to predict sigma h. And in the case of predictions for sigma h, yeah, we can try to forget about using these GNNs for galaxies. We have tried many things. And here I'm bringing two attempts that we have done. The first one was trying to do this GNN prescription, considering only the velocities of the galaxies and stellar mass. And we are not able to do predictions because we are really focusing on the peak of the distribution. And the same happens, or something more or less similar happens for trying to considering only the halo mass for each halo that the galaxies are living inside. And even though things are not working. So there are many attempts to explain this. First, these boxes are really small. Even if we try to do an MCMC and estimate the power spectrum, it's really, really hard to estimate sigma h for these small boxes. Maybe this can be an explanation. Another thing should be related to the fact that we are only using galaxies which are in the redshift 0. Okay, we don't have the final answer. But then there are some other works in this Camel's collaboration that indicates that considering boxes which are larger and considering summer statistics as input to do these machine learning things, we can try to infer sigma h, but not with these GNNs, at least not by now. So in order to try to put these things working on real data, we have been trying to see if we try to mimic real observation effects into these galaxy catalogs, we could be able to really estimate a megamatter. And we thought about many things. We thought about trying to artificially include some mask effects, trying to take care of velocity errors, or even trying to think about color, some galaxy selection, for instance, only consider red or blue galaxies. We trained this GNN and see if we could take care of these effects. And well, the results are not perfect, but they're kind of promising. Because if you think about all these predictions, and especially if you think about robustness, we kind of like have good predictions, okay? Especially if you think, for instance, about the blue galaxies or for smaller perturbations for the velocities. Well, of course, every time that we think about machine learning, and we are presenting this for a traditional community of cosmologists, we can try to think about what is going on behind the machine learning algorithm. And here is just an attempt of see this. And we're trying to predict an equation to really translate all the information that we're using as input to see what the GNN is doing. So I don't know if you have heard about symbolic regression. This is another way of doing machine learning, which means that we're trying to guess an equation to kind of like represent the machine learning. So we have like x0, x1, and so on, like as input information. And then we're trying to guess the mathematical operations behind these input variables, and ended up with an y equation, which is is going to predict like omega matter, for example. So this is known as symbolic regression. And most of the times this is done with genetic programming. And you can think about the mathematical operations that you can really think about using. And instead of like only trying to obtain an equation to really guess omega matter just per se, we're trying to replace what is behind our GNN. Okay? So remember the way that we're trying to update the parts of the graph? So we're trying to replace the edge model by an equation, the node model by another equation, and the final MLP by another equation as well. And this was done training the GNN on halos from Gadget. And here, guys, we can see the estimations for our GNN just by like the GNN using the halos. So here is for Gadget. And as you can see, the results are even better than the ones that have galaxies. And the other thing is like what is going on using these analytic functions, using these equations. And these equations are doing a pretty good job, right? But the interesting should be try to take a look at the equations that we found. And yes, sorry, this is not easy. So we are trying to translate a really complex graph neural network, right? So we don't have only one equation. And then second, we have one equation for each layer and for each part of the GNN. But it's kind of interesting to see the input variables that we have here. For instance, we can see that we have difference for the velocities of the halos that we have thought about, right? And maybe this could be related to a way to think about local gravitational forces that we have. Maybe we can see there that we have the distance modulus or the angles that we have used as input. And maybe we can guess that this distance is giving information about the density that we have, like the halos there. Maybe this angle is saying for us about the filamentary structure that we have there. Or maybe these are not only maybes, but if this really works, this can be the case that we're really interpreting that the GNN is using only gravity, only positions and velocities. So these are the predictions for halos from all these different any-body simulations. And then we can see the same working for halos from these different hydrodynamic simulations. So this was trained on Gadget, and this is working for all these other any-body and for all these halos from these hydrodynamic simulations. And at the time that we achieved these results, we're like, oh, this is really, really amazing. Because all these any-body simulations should be different approximations, but to solve the same kind of equations. We don't have anything like in the hydrodynamic simulations where we have different subgrid physics models. But then this is working even for galaxies. So yes, like these machine learning models are so powerful that in some sense, no matter the objects that we are using as input, we are always getting good predictions. So,
can you go back a little bit to the equation part then?
yes.
So how do you deal about with possible situation of overfitting or that you have like
Oh, yeah. So we can just disregard the
possible
equation.
errors in this equation?
Sorry?
You can have the possible equation there, but the
Mhm.
equation should have some error assigned to it.
Yeah. Of course, we have to think about, oh, what kind of error are you talking about? In machine learning, you have an rhetoric, systemic error, and so on and so forth. But okay, the way that we have done for finding these equations, we're like trying to see the simplest equations that give for us the best set of results for considering the metrics, right? And if you think about like doing different realizations of this, indeed, in some sense, we still have like more than one component here. You have to think about the fact that we have the MLP, and then we have like variations related to the MLP, and not only for the equation, because in some sense, we still have like there. But sorry, I don't know if I answered your
No,
question.
these equations there are getting obtained from some fitting in the simulations, or like from
Like the input data are the halos from the simulation.
you train the system to get these equations,
Yes,
but these equations could be also potentially be overfitted over the simulation that you trained it with.
overfitting the simulation or overfitting?
Overfitting the formulas. The equation that you're using might be overfitted to the training sets.
Overfitting in the sense of machine
I'm
learning
not
or?
worried about the errors that you could have in these potential equations. I don't think.
Oh. So there are many ways to interpret it and to try to answer your question right now. But if we have like, oh, sorry. If you come back to this and see that these equations are doing almost or something like kind of like even better job than the GNNs. So the error should be in the same level of magnitude, right?
Yeah. I think I'm getting confused.
Yeah, sorry, maybe I was
Confused
not
part.
understanding your
No,
question.
no, it's fine.
Sorry. And well, so this is working even for galaxies. And then like, these are just like the takeaway messages from everything that we have been thinking about. The first thing is like, these GNNs can be another way to do cosmology, maybe, but we cannot forget that we need training sets, right? Still, so if you think about estimating the parameters, using traditional cosmology, we still need random simulations to have the covariance matrix. So in some sense, to train everything, we still need to think that we have to have data. But if we were doing a good job, maybe this can be an alternative way to do cosmology, not the final way, right? The networks are truly like interpreting everything which is in the phase space information. We have shown this just taking a look at only positions, only velocities, or thinking about this universal equation. And then finally, we could show that we can handle some observation effects. Maybe we could handle systematics, real systematics for real surveys. And maybe we could really use GNNs to do the next estimations of the cosmological parameters using real galaxies. Yeah, so these are the final messages.
Once like you want to connect this with real data, then you also have to look at the other observables like redshift and angular position instead of like positions in 3D space.
Yeah.
Like, do these observables, can they also give the same results?
Well, the first thing is trying to think about the way to build the graph with this real data, right? If we could build a graph, probably this should be compatible with what we have done. And then this could work, but this is just a guess, right? There are like many things. I mean, the way that we have considered like the systematics is not perfect also, right? So there are many things that we have to think about before applying this on real data. But these are like preliminary results or a proof of concept that we could use GNNs to do cosmology.
Our link that you use there is a Cartesian thing, right?
Yeah.
But if you can translate that into redshift, RA and angles,
yeah,
then maybe there's no reason why this shouldn't work, except that you have to figure out a way of the getting the angles of the internal nodes of the graph. But
yeah, in the way that
should be done in principle.
Yeah, in the way that we could take into account all the symmetries and physical.
So I have a question about the discussion about super sample. So if can you remind us the size of the box that you use for training in Astro? It was the size of the small box is 25, right?
25 megaparsecs, yes.
Whereas Illustris TNG is 300 now.
200.
So that's megaparsecs, h minus one megaparsec.
Oh.
Right. So
yeah.
how many Astrid boxes can you fit inside the Illustris TNG 300?
Without repetitions, just
Yes, without repetitions, just
I don't know how many. Yeah.
many, right?
Yeah.
So if you ask what is the density fluctuation on a box of 25
Should be
megaparsec,
around 1.
I'm not sure about one, but it should be large enough that it would make a difference. So the question is this: if you get Illustris 300 with periodic boundary conditions, okay?
We,
And you get your Astrid also with periodic boundary condition, okay?
mm,
And if you get all the boxes inside of the Illustris TNG that you have with, then you estimate for each one of those sub boxes, then you take the average of that.
mm,
Isn't this much more accurate? Because if you're just making individual assessments of big little pieces of that large box,
yeah,
that those pieces inside there, they will have fluctuations, which are, I would guess, of order 10, maybe 20%. So some of that scattered, some of that additional, maybe you can show the plot there, which is, I think it's the next one. Right?
yes,
Yeah. What I'm thinking is that some of that scatter is just that you're sampling pieces of this Illustris box where the actual
then,
matter
yeah,
density there is higher or lower. And then, of course, you're comparing with the Illustris one number for omega matter, which is the mean.
Mhm.
So, of course, then you would have a different answer that has more scatter, but that's just because you're applying it to a single piece of that box. Isn't that the case, or am I misinterpreting?
no,
the
it
way
is,
that you-
it is the case, yeah,
Right.
because
So-
we are just like taking random sub boxes.
Right, but then what you have to do is that you have to compute what is the actual value of omega matter in that sub box, and not the mean value for the whole box. The
Yeah.
comparison is
The comparison should
it's
be-
unfair.
Yeah.
I mean, because what you would do in practice, that you would apply this to your whole sample and not just the small pieces.
Yes,
Right.
indeed.
So the fact that it's around the mean there means that you are doing a good job on mean, because that's what you would actually compute. It would be the mean of all those points there.
Yeah. Yeah, yeah, indeed.
That's the other thing, right? When you look at the plots of truth versus
Yeah,
estimation there, these are all for single boxes that have 25
megaparsecs. Yeah,
megaparsecs. If you have many more of those, then you would have a mean. And if your mean is not biased, then you would be even more precise. So what I'm saying is that there's a lot of variance in there, which you can eliminate by having larger boxes. And you would probably win in this way. So you would actually decrease the scatter, not increase by going to larger volumes. That's what I would expect.
I see. Yeah, indeed, this can be true, yeah.
I would try to just check that. I mean, the plot that you show there shows that, if it's what I understand it is, it's just that one Illustris TNG 300, and each one of those is a sub box, right?
Yeah.
Take the mean of all of that. That is your real estimate.
Yeah, there is, I took this and it
Right.
was like, I was really, really close to
Yeah,
0.3.
there you go. So that's your real estimate, right? This is what you would be doing as an observer, right? I mean, you train, you say, okay, this works, my simulation works fine, I can do it for halos or galaxies, it doesn't matter. I'm just finding a way of looking in phase space and deducting what omega matter is. If I have a big volume, I would apply to the whole volume
Yeah,
or to small pieces and then take the mean, which is the same. And then the final answer will be,
the right, like the good job, yeah. Yeah,
this is
Yeah.
how I would interpret your data, not just as, individual boxes there, which are,
yeah.
this one.
Mhm. Yeah,
So
but
just
yeah,
take the mean.
yeah,
Really,
yeah, true.
including all the outliers, everything, it doesn't matter too much.
Yeah. Because what we're like outliers here, yeah. Yeah, indeed. So this can handle super simple covariance. In some way. Yeah. Every time that we try to apply machine learning, of course, there is no like only one way to do things, of course. And there are many things which are really in some sense not able, like we're not able to truly explain, of course. But indeed, can be another way to do cosmology. And this makes sense.
Okay, Ricardo, you can ask a question now.
It's over.
What do you do?
No, no.
Oh, let me explain everything again. Yeah,
So first, thanks for the presentation. And I was really like excited to see the Sigma 8 results,
mhm.
because it's a very important parameter. And I was a little bit disappointed to see the Sigma 8 results, unfortunately. Wow, that's life. And from what I got from the presentation, one thing that limits these models to really work well in Sigma 8 is the size of the simulations,
In
right?
some sense, yes, because if you do this for plot, which is another data set because like cosmology for machine learning, especially, and then there are halos from 1,000 megaparsec boxes. Yes, we can apply that in Sigma H there.
So this might be a really dumb question, but would you try to predict instead of Sigma 8? Like you would need a larger simulation, and I don't think you have as much larger simulations as you have these simulations with 200 to 300 megaparsecs
You mean for hydrodynamic
for
simulations?
hydrodynamic. This might be really dumb, but could you try to estimate something like instead of Sigma 8, Sigma 6 or Sigma 5? I don't know.
Yeah, that's the point. I mean, it is like the raw machine learning answer should be, you have this as your number for each one of these boxes. If you have a good correlation, you can do this. But physically speaking, this can be a challenge. But yeah, Yep.
Just also a naive question, why do you always pick like one simulation as the training set? Can't you use like boxes from different simulations as the training set?
yeah, there's no specific answer to tell you, oh, the best way to do should be using many different hydrodynamic simulations and then have a really broader sample of what your universe should be and then get good estimates. The point is like many machine learning algorithms, no matter it's only GNNs or if you think about usual neural networks, maybe doesn't matter which machine learning algorithms think to solve a problem. The point is that when you use different simulations, even though you think about using, oh, I'm going to use 500 simulations from Astro, 500 from Simba, and 500 from Illustris-NG, sometimes what you can get, and this is not like only one answer, but sometimes you are biased to get better predictions for one of the simulations instead for the others. And we don't know if this is a matter of the physics which is in there, it's in some sense more important, or if it's something that, oh, we have a latent space which is like more inclined to get answers in that direction. We don't know. But if you train in different data sets, so different subgrid physics models, even though if you choose the same number, and then you're going to see the predictions in other boxes from these guys, sometimes you can get good predictions for one of the simulations instead of all of them. Because you have something which is like biasing your latent space direction instead of get good predictions for everything. But this is not like a final answer.
Any more questions?
So maybe have a general one. So right now that you've made all these tests, what is stopping you to move into real data?
What's sorry?
It's stopping you from moving to real data.
Oh, if I have like a survey where I can really have access, first this should be a peculiar velocity survey, because then I would have like, okay, I have to convince people to run many simulations. I don't know which one should be the best, but to run many simulations and to have these very, very broader variations and train my machine learning there. More than that, in the case of the GNNs, we have some memory issues. Because as we increase the number of objects, we are increasing the memory that we need because we have more nodes and more edges. So there are many things to try to think about and try to overcome.
So peculiar velocity is something that you really, really need, or is that something optional?
Uh,
In general, to get velocity reconstruction from galaxies where it's really difficult.
yeah, because we need both as far as we
Right.
could end up with this, right?
She only needs the relative velocity, right? So if you have large enough groups or clusters, then this is.
Right.
Or you need a good redshift, really.
Yeah,
Mm.
so. Should be.
So nothing is really stuff.
Yeah, I have to convince people, yeah,
Time.
yeah, maybe time.
I mean, you have the samples or galaxies data already, right? So at least a spectral copy if you want to use this.
Yeah, as this, yeah. But then I have to think about which should be the best method to get more, like, I mean, which should be the method to think about to have these simulations? It's probably not would be like the hydrodynamic simulations, right? Should be some approximated method. Which one should be the best? These are things which are in my mind. Are all these approximated methods really similar to hydrodynamic simulations? So yeah, nothing's stopping, but then there are many things to think about it.
Yeah, of course.
Anybody else? Okay, thank you, Natali.
So before we split, we have to decide the time, the dates for the next meetings. So between, yeah, September, maybe the 12th, sorry, 13th,
Yeah, the 20th I can,
you cannot.
no.
Okay. So the 13th with possible speaker, Walter.
I cannot do the 13th.
No, you cannot. So
I can do the week before, but maybe that's too early.
6,
6 is Semana da Pátria, but sure, works for me.